Okay, so oceanic current phenomena. We are not going to study all of those phenomena. Only those listed here. So ocean eddies and rings, undercurrents, and then we need to study also ocean currents and climate because there is a relationship. And then later on, we will study ocean current observations and current information by the use of stream drift chart, pilot charts, sailing directions, current atlases, and nautical charts. Hey, what are ocean eddies? Sometimes water spins away from a surface current, creating an eddy. So because the surface current, like the Gulf Stream, is very large, and it is not actually a straight current, some of its parts are also curving, going to the North Atlantic current. So sometimes water spins away from this current and creating an eddy. Okay, the swirling water of an eddy can be more than 100 kilometers or 54 nautical miles in diameter. The center of some eddies is cool while the center of others is warm. Marine life is sparse in warm water eddies where the water does not have many nutrients. But cold water eddies are usually full of nutrients and marine life. So there is a difference. It is better to have the cold water eddies. Eddies form when a bend in a surface ocean current lengthens and eventually makes a loop, which separates from the main current. The Coriolis effect causes cold water eddies to rotate counterclockwise and warm water eddies to rotate clockwise in the northern hemisphere, while in the southern hemisphere, cold water eddies rotate clockwise and warm water eddies rotate counterclockwise. There is evidence that the topography of the ocean floor can help eddies to form too. Once an eddy forms, the swirling waters last for at least a few months. So matagal siya sa dagat. So if you can see this one, if I may enlarge it, this is a satellite image of the ocean. So you can see some part. There are eddies. Ito, you can see. So nakita nyo, paikot siya, no? But of course, you cannot see it clearly because this is a satellite image. Okay, the ocean is a huge body of water that is constantly in motion. General pattern of ocean flow are called currents. Sometimes these currents can pinch off section and create circular currents of water called an eddy. So it is a circular current, the eddy. No? So maybe you have seen also this one. Sometimes you can see in the river. Also some swirling of the water. So that is also an eddy. Kahit sa baha, minsan, you can see that also if you have experienced flooding. When I was a kid, because our house is a little bit near the river, during typhoon, sometimes the water is buti second floor, may second floor kami, the water reaches up to the almost up to the second floor. So from the balcony we can watch the flood. So I saw these eddies before, no? Swirling. Okay, you may have seen an eddy if you're ever gone canoeing and you see a small whirlpool of water while you paddle through the water. The swirling motion of eddies in the ocean cause nutrients that are normally found in colder, deeper waters to come to the surface. So this is also the same as upwelling, where the water from the bottom of the ocean rise above the surface and bringing nutrients for fish, for food chains. No? Okay, significant eddies are assigned names similar to hurricanes. I know you have studied how to name hurricanes. So also the eddies, they have names. Although this is not an important topic, naming of eddies. But they are doing it in the US. An oceanographic company called Horizon Marine assigns names to each eddy as they occur. The names follows chronologically along with the alphabet and are decided upon by staff at Horizon Marine. Okay, the staff try to think of creative ways to assign names. For example, an eddy that formed in the Gulf of Mexico in June 2010 is named Eddy Franklin, after Ben Franklin, as he was known to have done research on the Gulf Stream. Okay, next is the ocean ring or the ocean rings. The largest and more energetic eddies in the ocean are rings that shed off the Gulf Stream. Rings are an important component of the Atlantic circulation. A ring is a type of mesoscale eddy that forms when Gulf Stream meanders break off the stream, creating independent circulatory systems. The formation of a Gulf Stream ring is the only way that warm tropical water located south of the Gulf Stream can be moved north of the Gulf Stream. Ring formation is also the only way cold nutrients-rich shelf water located north of the Gulf Stream can be moved south of the Gulf Stream. Therefore, ring formations are very important way for the ocean to distribute heat and energy. So ocean rings is also an eddy, but they are more prominent because they are large and more energetic. Okay, there are two types of Gulf Stream rings, warm core rings and cold core rings. Warm core rings form of a northward bending meander and are always found north of the Gulf Stream. Cold core rings form of a southward bending meander and are found south of the Gulf Stream. Rings play an important role in transferring water across the strong frontal boundary of the Gulf Stream. The Gulf Stream can be accurately thought of as a barrier between the cold waters of the north and warm waters to the south. The formation of a warm ring results in unproductive Sargasso Sea water transferred into the productive waters of the continental margin. So later on, I will show you a map of the Sargasso Sea. Warm core ring formation results in Sargasso Sea water being transported into continental shelf water. This is the only mechanism to transport surface waters across the Gulf Stream. A mesoscale is an intermediate scale, especially that between the scales of weather systems and of microclimates, on which storms and other phenomena occur. And meander is a circuitous journey, especially an aimless one. Okay, during an average year, 10 to 15 rings are formed. The rings are usually between 150 to 300 kilometers in diameter. So malaki siya, di ba? 150 and 300. And can have rotational velocities over 1 meter per second. Okay, so can you convert 1 meter per second to nautical miles? So later I will show you. Or just note about the conversion. So just divide it by 0.51444444444. Walang cut-off ng 4, no? So that is the conversion anyway, maybe I will add here the conversion for you to remember when you go on board. Kasi even the officers, some of them do not know how to convert meter per second to knots. No? So wait, let me try to write here. Okay, one knot is equal to 1 meter per second. So pag knots to meter per second, multiply mo lang by mali ako, sorry. 0.514444 meters per second. So just multiply it by this value, then you will get meters per second. So if you are going to get knots from meters per second, just divide, no? So divide mo naman. Or you can use the other conversion, which is 1 meter per second is equal to, okay, just multiply with that, no? So you can divide it vice versa. Sakali, 1 meter per second divided by 0.514444, you will get knots. Also, 1 meter per second, multiply it by 1.94384, you will get also knots. So yan ang conversion, no? Which is it's good for you that you have learned here in Lima, because I have been with other officers, di nila alam, no? They do not know how to convert knots to meters per second and vice versa. Okay, cold core rings also are reabsorbed into the Gulf Stream, but they may have life cycles of several years, since they may drift far into the Sargasso Sea before eventually drifting near the Gulf Stream again. Cold core rings often lose their identity on satellite images due to the intense heating of the surface waters south of the Gulf Stream. Since the satellite can only measure the surface temperature, these cold rings often become masked by warm surface layer. Cold core rings are the ocean's equivalent to an atmospheric low pressure system, and thus are often referred to as cyclonic eddies. Gulf Stream rings often exhibit large vertical structure and may extend several kilometers deep. So malalim siya, no? It may extend several kilometers deep. Biluin mo kung gaano kalalim 'yun, no? Okay, so I borrowed a image from the marinecoastal.edu. Okay, so the black one is the island, no? So this is New York, Boston. The Gulf Stream is here, collecting to the North Atlantic current, and also to the Norwegian current later on in Europe. So if you can see, this one is the Sargasso Sea. It is part of the western or the western part of the Atlantic, North Atlantic Ocean. So this is also a satellite image, so you can see the warm core rings. Okay, here's another map of the Sargasso Sea with an arrow in pink showing the current, the circulation of the current. Okay, next is undercurrents. The ocean is connected by a massive circulatory current deep underwater. This planetary current pattern, called the global conveyor belt, slowly moves water around the world, taking 1,000 years to make a complete circuit. It is driven by changes in water temperature and salinity, a characteristic that scientists refer to the current as an example of thermohaline circulation. I have explained the thermohaline circulation during our first part of our lesson. So later on, I will put a video in our LMS regarding this conveyor belt. So just for you to watch and to be informed by what is happening. No? This is also a phenomena, biruin mo, no? Because the water will be on this cycle and it will reach the starting point in 1,000 years. Okay, both heat and salt contribute to the ocean water's density. Saltier and colder water is heavier and denser than less salty or fresher, warmer water. Around the globe, there are areas where the heat and saltiness of ocean water and therefore its density change. The most important of this area is in the North Atlantic. As warm Atlantic water from the equator reaches the cold polar region in the north via the Gulf Stream, it rapidly cools. This region is cold enough that the ocean water freezes, but only the water turns to ice. As the water freezes, it leaves the salt behind, causing the surrounding water to become saltier. So, pag naging yelo, yung dagat, only the fresh water or part of it will freeze and it will leave the salt in the surrounding waters. So the surrounding water becomes saltier and saltier. So the cold salty water then sinks in a mass movement to the deep ocean. It is this sinking that is a main driver for the entire deep water circulation system that moves massive quantities of water around the globe. Cooling also occurs near Antarctica, but not to the extremes that happen in the northern hemisphere. So this is also a miracle, no? As you can see, that's why some scientists do not believe that God exists, but how would you explain this phenomena? No? Perfectly done. So here, no, the deep water formation in the Arctic, and also here caused by the Erminger current. So this is the Gulf Stream, di ba? And then when it will go up, it is called the Erminger current. When it will continue, it will go to the Norwegian current, which brings warmer climate to Norway. And then, so this deep water formation, when the water is cool, it becomes colder and colder and it freezes. So when it is frozen, the salt remains on the surrounding seas. When the water sinks, this will become a driver to drive the deeper currents, which is in blue color. So this cold water will move in this direction, in this pattern, going to the Southern Ocean, and then going back again to what they call this, the coast of Africa. Although this is, of course, undercurrent, because here, if you can remember, the Madagascar current or the Mozambique current and also the Agulhas current, they are very strong going down or going to the polewards. So, yun pala, beneath them, there is a deep water current, which is cold current that exists. So this is the pattern. It will go back again to the surface, and then it will flow towards this, and also here, going connected to the Guyana and the Caribbean current, and then going out of the Gulf of Mexico to form the Florida current and the Gulf Stream. So ito na naman, Gulf Stream, balik na naman siya. So this is a cycle that will be completed in 1,000 years. Okay, another area of the ocean where massive amounts of water move to the ocean's depths is in the Mediterranean Sea. In this area, evaporation is the main driver that changes the salinity of the ocean water. Now, this is not caused by any stream or any current, but the main driver is evaporation. It means mataas ang evaporation doon sa Mediterranean Sea. So as water in the Mediterranean evaporates, it leaves the salt behind. This super salty ocean water then bleeds into the Atlantic via the thin mouth of the Mediterranean, also known as the Strait of Gibraltar. But remember, no, I explained in our last meeting that in the Strait of Gibraltar, the current is going, the surface current is going inside. So it means it is in eastward direction. But this undercurrent is going out because that is the only opening going to the Mediterranean Sea, the Strait of Gibraltar. So this undercurrent is going out of the Mediterranean Sea using this also, but under the surface. That's why it is called undercurrent. So nagsasalubong sila doon, ano, yung ating yung surface current and the under or deep current. So that is also very hard to explain, no, how perfectly done by God, no. Okay, when cold salty water circulates the globe and gradually becomes warmer, it begins to rise. The old deep water is full of nutrients that have accumulated from the sinking of waste from the productive surface waters up above. Locations where the old water rises are highly productive areas because they contain ample nutrients and have access to sunlight. The perfect combination for photosynthesis. The effect of the ocean current in climate. So the great ocean currents, like for example the Corusio and the Gulf Stream, they are climate engine because they also affect and change the climate in the area that they deliver the warm water. Ocean current transport enormous amount of heat around the world. This makes them one of the most important driving forces of climate because they respond extremely slowly to changes. the effects of global warming will gradually become noticeable, but over a period of centuries. Climate changes associated with wind and sea ice could become recognizable more quickly. Okay, what drives the water masses? Water plays a central role in the climate system. Its density varies depending on salinity and temperature. Cold, salty water is heavy and sinks to great depths. This causes the circulation of the million of cubic meters of water in the ocean. This powerful phenomenon, which primarily occurs in a few polar regions of the ocean, is called convection. Okay, the surface water in North Atlantic region sinks to a depth of around 2,000 meters due to convection. There it settles on an even denser deep water layer from the Antarctic that extends down to the seafloor. As the cold and salty surface water sinks by convection, salty water flows in from nearby warmer regions from the direction of the equator. This water is then cooled in the Arctic air and also begins to sink so that the convection is continuous. Before sinking, the water absorbs enormous amounts of gases such as carbon dioxide at the sea surface and then transports them rapidly to much greater depths. Low temperature and high salinity are the primary driving forces of convection. They pull the dense water of the polar regions downward, which drives a worldwide convection engine called thermohaline circulation. So I have explained this also in our first meeting. The thermo means driven by temperature differences. And haline is driven by salinity differences. The cold salty water submerges primarily in the Labrador and Greenland seas. And then flows southward towards the equator and beyond. Although convection only occurs locally in the polar regions, it propels thermohaline circulation, which spans the globe like a giant conveyor belt. Even the Gulf Stream and its branches are driven by convection and thermohaline circulation. Although wind also influences the transport of water masses, its contribution is significantly less. So there is a conveyor belt, which is, I have shown also the map already, but I have another one later. Okay, but how do the water masses of different densities that drive ocean convection actually originate? So air temperature, evaporation, and precipitation are among the most important factors in the answer to this question. The freezing of water in the polar convection regions also plays a central role. Because ice only contains about 5/10 of a percent salt, it leaves behind a considerable amount of salt in the water when it freezes, which increases the salinity of the surrounding ocean water and thus increases its density. The water mass produced by the convection is in the Arctic is called the North Atlantic Deep Water, NADW. Okay, convection also occurs in the Antarctic regions. Because of their even higher salinity, the water masses produced here sink all the way to the seafloor. This is called the Antarctic bottom water, AABW. So I do not know why AABW, but it is only Antarctic bottom water. So I suppose this is Antarctic area bottom water. So, but let us leave it like that. Antarctic bottom water and AABW. And it flows across the ocean floor, halfway around the globe into the North Atlantic. The AABW is also the deep water layer of the thick intermediate North Atlantic uh, deep water overlies when it sinks by convection. The NADW forms in the Greenland and Labrador Seas schematically illustrates its flow path and the return flow of warm water in the near surface layers. In the global conveyor belt of thermohaline circulation, the North Atlantic deep water and especially the Antarctic bottom water remain in the deep ocean for an amazingly long time. Radioactive carbon isotope dating of the deep waters indicate that from the time of sinking into the deep until its return to the surface, a period of several hundred or even up to 1,000 years will pass. So they have observed it like that, no, for how many years? Okay, for most of this time, the water remains in the colder deep regions of the thermohaline conveyor belt because there the flow rate is slow at around 1 to 3 kilometers per day due to its high density. The amount of water involved in this cycle is truly immense. Its volume is around 400,000 cubic kilometers, which is equivalent to about one-third of the total water in the ocean. This is enough water to fill a swimming pool 400 kilometers long and 100 kilometers wide and 10 kilometers deep. The Oceanic conveyor belt transport about 20 million cubic meters of water per second, which is almost 5,000 times the amount that flows over Niagara Falls in North America. So ganun siya kadami, no, yung dinadalang tubig. Okay, so this is another map of the thermohaline circulation, or this is called the global conveyor belt. So here heat is released to the atmosphere because of the cooling of the warm waters here in the Labrador Seas and in Greenland. No? So because of that, I have explained already before that the water will freeze and leaving most of the salt into the surrounding sea. So the surrounding sea becomes saltier and thus heavier. So it will sink and it will drive this global conveyor belt. So that is the direction. Ano? Okay, the worldwide ocean currents of the thermohaline circulation system are extremely complex. The flow of cold saline surface water, which is in blue color, downward and toward the equator can only be clearly recognized in the Atlantic. Warm surface water, red, flows in the opposite direction towards the pole. In other areas of the current relationships are not as clear-cut as they are in the Gulf Stream system between North America and Europe. The circumpolar current flows around Antarctica and thus so throughout the total depth of water column. The small yellow circles in the polar regions indicate convection areas, and the dark areas are characterized by high salinity and the white areas by low salinity. Salty areas are mostly located in the warm subtropics because of the high evaporation rates here. Okay, ocean eddies, an important climate component. In addition to the large conveyor belt of thermohaline circulation, heat is also transported in the ocean by eddies, which are analogous to low pressure systems in the atmosphere. But they are significantly smaller than the atmospheric low pressure systems, which can often be several hundred kilometers wide. These mesoscale eddies form when water flows between regions with large density or temperature differences. They can be clearly recognized on satellite photographs. Investigations have shown that they not only occur at the ocean surface as, for example, in the North Atlantic area, but can also be located at great depths of thousands of meters, for example, off the coast of Brazil. Because of their strong influence on the large-scale heat transport, these deep sea eddies also play an important role in long-term climate processes. But we will not study all of those processes, of course, because only these information are enough for us to know because we are not oceanographers or scientists. Okay, current and change. Because ocean circulation is driven by temperature change, any variation to the planet's climate could significantly alter the system. So scientists worry that the melting ice caused by global warming may weaken the global conveyor belt by adding extra fresh water in the Arctic. A 2018 study found that the massive ocean current that courses around the Atlantic Ocean, called the Atlantic Meridional Overturning Circulation, has decreased in strength by about 15% since 400 AD and is now the weakest it has been in 1,600 years. Ironically, despite an overall increase in global temperatures, many places in North America and Europe may get colder as a result. Some places will become colder because of the weakening of the global conveyor belt. Okay, so that is the end of our lesson for today. You can take the quiz now. You have enough time. Okay, gentlemen, thank you for listening. Okay, so you can go to the LMS and take the quiz and tell me if there are any problems.